So for the next function that we're going to be transforming is something called absolute value functions, which is where we say that f at x is equal to the absolute value of x. And what this absolute value means is that we negate any minus or plus. So we just take the absolute numbers. If it's, let's say, -2, then we just treat it like a 2. If it's -3, we just treat it like a 3. So the regular function, or the parent function, is f at x is equal to absolute value x. And the transform function would be f at x is equal to a, and then the absolute value lines b times x, if there is a b value, x minus h plus k. Just like our other transformation algorithms, your a and b are factors by which things get stretched or compressed. So your a refers to a vertical, or not vertical, but vertical stretch or compression. And then the b would be a horizontal, right, stretch or compression. So just write S or C, stretch or compression. And then of course your h, just like our other transformation algorithms, h and k are translations. If h is negative, then it moves to the left. If h is positive, then it moves to the right. And remember that this equation over here is set to 0, or gets set to 0. So if we say that it's x minus 3, well, it's really x equals 3. Because when we bring 3 to the other side, it becomes positive, which means it would really shift right. Now when it comes to the k value, negative value means it shifts up, and then positive value means it shifts down. So I always find the best way to attempt these is to first figure out what does the parent function look like. So let's say I have values 2. I got a table of values here from 2 all the way down to -2. Unlike our root function, we can use negative numbers. We wouldn't get undefined or a syntax error or anything like that when it comes to absolute value. What it does mean, though, is that because it's absolute, we don't really count the negative. So for example, if I go f at x, let's say for the first one, f at x is equal to absolute value x, which is equal to absolute value 2, well, that just equals 2. So I plug in 2 over here. Now, let's say if I did -2, and I go f at x is equal to absolute value -2, right? So this x input. Well, remember, those lines tell us, the ones over here, that we negate any positive or negative signs, so we just write 2. So once again, over here, I'm going to erase this a little bit here. Whoops. We can rewrite it. This would be 2. This would also be 2. And so whatever the x input is, whether it's positive or negative, your y is going to be that value. So if I go f at x is equal to absolute value 1, 1, this is 0, and then same thing, f at x is equal to -1 absolute value, which is really just going to be 1 if we neglect the negative. So this is our parent function table, and I'll erase the bottom over here. So we're going to plot this to see how we can expect the parent function to look, at least for the first couple of points. So at +2 for the x-axis, it'll go to +2y. So we got a point there. +1 for x is +1y, and then 0 is 0. And then when it comes to negative, for -1, y is +1. For -2, y is +2. And so connecting our dots, oops. Okay, we have a function that kind of looks roughly something like that. And I'm going to do that to the other side. And roughly something like this. Okay, and remember, we really just look at the first 3 points. So let's say, bearing all this in mind, we want to graph the function f at x is equal to -3 absolute value x plus 1 minus 3. Well, what we're going to do here is, just like we see in the transformed algorithm, we're going to identify the A, B, if there is one, H, and K. This here would correspond to your A, and because it's got a negative, we know that there is a reflection over x-axis. So we should see this function be flipped like this. And it's greater than 1. So what that also means is that there's a vertical stretch. So it should look a little taller, or at least, well, yeah, basically just look a little taller, or longer. Now, the B value appears to be 1, so there's no B value, no change. Right, so let's write B is equal to 1. Now the H value, because it's positive here, it's really going to be a negative 1, which means that it shifts left. Okay, so all my points are going to shift towards the left by 1 unit. And then of course the K value over here, which is outside the incomplete brackets, that's going to be minus 3, which then means that the whole graph shifts down. Okay, so what I'm going to do here is apply my transformation algorithm to each of these points, and when we do that, we should get new points to plot for these. So with that in mind, let's get started. So for the y values, remember that the y transformation algorithm is always going to be a times y plus or minus k, depending on when k is negative or positive. And so I'll do one here, and then we'll fill in the table. So we're going to go y prime, the new y value is going to be equal to a, which we said was 3, but it's a negative 3. So we're going to write negative 3 times the old y value of 2 minus 3, right? The k value over here. So when we plug that into the calculator, this is minus 6 minus 3, y goes to negative 9. So I'm going to scratch out that 2. Negative 3 times 2 is negative 6 minus 3. And that gives us 9, and this is going to be minus 9. And then I'll do the same for the one below it, where we have, once again, y prime is equal to negative 3 times 1 minus 3. Negative 3 times 1 is negative 3. And then negative 3 minus 3 gives us negative 6. So I'm going to cross that out and put negative 6. So plugging in that equation a repeated amount of times, we end up getting these following values: so negative 6, negative 9, negative 6, negative 3, negative 6, negative 9. Now we're going to apply the same transformation equation to the x's here, but we'll do to the first couple. So here, remember that x prime is equal to x over b plus or minus h, depending on whether h is positive or negative. So we're going to go x prime is equal to the x value. Let's say we start at the bottom here. It'll be 2 over, we said that b was 1. And then plus or minus, now in this case, the h is negative 1. So we're going to go minus 1. And that's going to give us a value of, we're going to go 2 divided by 1 minus 1. That gives us a value of 1. So I'm going to cross out the first value and put 1. Okay. And I'm going to apply this formula to the rest of the x. And so applying this algorithm to each of these points, I end up getting 1, 0, negative 1, negative 2, and negative 3. So now what we're going to do is we're going to plot each of these and see what our transformed function looks like. So our first point over here, we have a point at 1 and negative 9. So I'm going to extend this graph just a little bit to make sure it hits the negative 9. So when x is 1, we have y at negative 9. Okay, so 1, and then we go down 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we got this. Okay. So 1 negative died. Okay, when x is 0, the y is negative 6. So at 0, 1, 2, 3, 4, 5, 6. So we'll put a point here. When x is negative 1, y is going to be negative 3, so it'll be negative 1, 1, 2, 3. So just like this. Okay. And then when x is negative 2, so over here, y is going to be negative 6. We'll go 1, 2, 3, 4, 5, 6. So we'll put another point over here. And then when x is negative 3, so just over here, y is going to be negative 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, connecting the dots, we get something that looks like this. We can see that the graph has been flipped, which is why it's turned upside down. It's been flipped over the x-axis. And we can see, just like the equation tells us, that it's about 3 times as long. If we count the original function height, if we go from point to point, it had a height of about 2. Now when we go from point to point, if we count the squares from this point all the way to this point, we have 1, 2, 3, 4, 5, 6, which is exactly 3 times greater. And so, similar to our previous functions, using the transformation algorithms, we can also easily translate an absolute value function. So let's say we reverse the question and we asked you, what is the equation for g at x, which is the blue transformed function from the parent function f at x. So similar to how we were dealing with it before, what we're going to do is we're going to see by either picking a point, we're going to substitute, use a little bit of algebra, and then see if we can pick off A, B, H, and K. So the first thing we're going to do is write down as much as we can. Remember that this is the transformation algorithm here, plus or minus K. And we could see a couple of things. First of all, we could see that there is a reflection over the x-axis. So if there's a reflection over the x-axis, then we know that A is negative. So A is negative because the graph has literally been turned upside down, right? It's been flipped. And if it's been flipped, what we can also understand is that this and this must be the same point. So we're going to use it as our reference point to help us determine the rest of the equation. Now, using that point, I can see, okay, that the first point here has been shifted 1 to the left. So in the equation here, I can write that y is equal to a x minus 1. Now I'm going to write, if it's shifted to the left, it should be plus 1. In addition to that, if it started at 0, it's 1, 2, 3. It's been shifted 3 units down, which means that the k is minus 3. Now, for the b, what we can do is we can count how many squares the original parent function is and compare it to how many squares from point to point the transform function is. When we look at the parent function, it's 1, 2, 3, 4. If we look at the transform function, it's also 1, 2, 3, 4. So we know that our b value is going to be 1. And so we could just write that down over here, but really there's not much change to it. Now, I have y is equal to a x plus 1 minus 3. Now, how much did this stretch by? Well, I can pick any point, and I could use the initial point that I highlighted in green over here, which I'll now highlight kind of in yellow. And we can sub in those values of the new point and then isolate for a algebraically. So at that point, we see that when x is negative 1, y has a value of negative 3. So we're going to go for the y value, and I'll scroll up a little bit. We're going to go negative 3 is equal to a absolute value of negative 1 plus 1 minus 3. Now, negative 1 plus 1 gives you a value of 0. So we got negative 3 is equal to a. There's nothing here, so we got a minus 3. Now, here's one thing to remember, is that I know that the x value here is negative 1, but this is an absolute value bracket. So anything we plug in for x has to be taken as the absolute value. So instead of writing negative 1, we have to write 1 plus what? Minus 3. Now what I'm going to do here is with that 3, I'm going to move it over to the other side. And that's going to give us this value here. So we're going to go, so what plus what is going to give us 2. So we got a. And then remember that this here is not a multiplication sign. It's not really a bracket. So we could really open it up. And I said that I was going to bring the 3 over, but that was a mistake. Actually, I'm going to open up the bracket here. It's not really a bracket, but it's really a, and then 2 minus 3, which is minus 1. And we can just remove that and write a minus what? Because 2 minus 3 is minus 1. And then if I bring the minus 1 over to the other side, negative 3 plus 1 gives you a, which means that a is going to be equal to negative 2. And so our function would then read like this: y is equal to negative 2, x plus 1 minus 3. And if we check our original height, the original height of our parent function from point to point is 2 units long, right? We could see it like this. It goes down 1, 2. Now if we look at the transform function from point to point, it goes 1, 2, 3, 4, which is exactly a value of negative 2. And so one of the things that I do want to stress here is that when we solve this here, we sub it in, right? Whatever you plug in at x, it has to be an absolute x value. So 1 plus 1 is 2. And then it's not a multiplier. So we're not multiplying the 2 to the negative 3. So we're going to open it up and go 2 minus 3, which gives us negative 1. So it's like an a minus 1 on this side. And when we bring it to the other side, negative 3 plus 1 gives us negative 2.